Okay, hello everybody. Um, so, in the previous lecture, we started off with the towards showing that uh, the computation of f0, that there is a zeroth frequency moment. In other words, the number of distinct elements uh, for um, for the approximate computation. The approximation being when it is approximated to a factor of 1 plus minus epsilon requires requires so the f0 estimation, we know that it can be done in order 1 by epsilon square times this log n plus log m log 1 by delta space, but we are going to show that this 1 by epsilon square term here is, or the factor here is essential, right? We cannot remove that. So in fact what we are actually going to show is that the 1 by square root and approximation, sorry, 1 plus 1, 1 plus minus 1 by square root and approximation requires linear space, right? So that is a extreme situation when epsilon is 1 divided by square root n, right? And what we do is we use a reduction from gap Hamming problem to f0, right? We went through the details of that. So so the estimation of f0 that we want to say is uh, requires a linear space. That is a probabilistic and approximate estimation. So if such an estimation is done, the prob the resulting protocol for gap Hamming will also be a randomized algorithm. So what we want to complete this, so we saw this reduction. What we want to actually complete the proof that f0 estimation requires linear space is to actually show that the gap Hamming problem requires, even in the randomness setting, in the randomized setting, uh, requires linear uh, number of bits to be communicated, right? So that's what we are going to see today. We are going to see that the randomized complexity of the gap Hamming problem, where c is equal to 4, is linear, and we are going to show it with public randomness. So because if we show this for public randomness, then obviously this holds true for private randomness also. So again, just to recall, the problem of gap Hamming problem is gap Hamming of c, and the parameter is c, is 1 when the Hamming distance is low and 0 when the Hamming distance is high. What do I mean by low? Low means Hamming distance is less than n by 2 minus c square root n, and high means greater than n by 2 plus c square root n. And it's a gap version of the problem, or a promise version of the problem. So we don't care about what the protocol outputs if the Hamming distance is in between. In other words, the problem instance holds this promise that it is going to be the low case or the high case. There is no in between case. Right? So that's the gap Hamming problem. It's called gap Hamming because it's a gap that is promised. And now we are going to see that the randomized complexity, the randomized one round complexity, not randomized complexity alone, because the f0 reduction here would imply a one round protocol. So what we are going to see is that the one round complexity of gap Hamming problem is going to be linear, requires linear number of bits, linear many bits. Okay, so what we are going to do is, recall in lecture 28 we had shown a lower bound for the index problem. The lower bound was that the randomized one round complexity of index was linear, right? So we showed that the randomized one round complexity of index was linear, and right, this used for this we constructed these. We had this Hamming distance based argument, and we drew balls around the answer vectors and all that, right? So we showed that the randomized one-round complexity of index is linear, is at least linear. So to prove the gap Hamming lower bound, we are going to use a reduction from index, and it is going to be a randomized reduction. Okay, and this reduction will not use any communication between Alice and Bob, and this reduction is going to rely on the shared random bits. What is going to happen is that given an instance of index to Alice and Bob, they will construct an instance of gap Hamming without any communication using only the shared randomness. And what is very interesting or fascinating about this reduction is that the instance constructed will be positively correlated, or will have a, when I say positively correlated, in other words has low Hamming distance if the answer to index is 1, and they are negatively correlated, or will have a high Hamming distance if the index instance evaluates to 0. Right? The gap Hamming instance has low Hamming distance if index is equal to 1, and high Hamming distance if index is equal to 0. And this is achieved without any communication between Alice and Bob, and only using the shared randomness. So let us see what happens. So Alice and Bob are going to generate inputs. So they are given an instance of index, and they are going to generate an instance of Hamming distance, gap Hamming problem, and they generate this instance of gap Hamming problem bit by bit. So first, Alice and Bob are going to generate one bit each for each one of them, and then another bit each, and then another bit each, and so on. So let us just see how they generate the first bit for both of them. Okay. So what they do is, given x and I, which is the instance of index, Bob simply looks at, so Bob knows I because that's his input. Now so they both look at the first n, so they have the infinitely long random bit sequence. So they both look at the first n bits of the random sequence, right? Bob looks at the ith bit of that random sequence, and his input is b, which is the ith bit of the random sequence, which is ri. He sets b equal to ri. So in some sense, they are both going to treat the first n bits, the n random bits as the input. So Bob is going to treat the n random bits as Alice's input, right? So the answer is xi, but since he doesn't have access to x, he's going to pick ri. And Alice is going to check what is the Hamming distance between x and r. Right? Alice knows x, she doesn't know I, but she has access to r. R means the n random bits. She checks the Hamming distance. Is the Hamming distance strictly less than n by 2, or is it strictly greater than n by 2? Just one word of note here. In this reduction, we pick n to be odd. Okay, so that we don't have to deal with the mess of what if it is equal. Okay, so we just choose n to be odd. So either the Hamming distance is strictly less than half or strictly greater than half. We don't have the equal case. In this case, so if it is strictly less than half, in this case, they output Alice sets a equal to 1, and in the latter case, Alice sets a equal to 0. So the intuition here is that Alice is checking how close is r and x, how close are x and r. If the Hamming distance between both of them is small, then she is going to say 1, and if the Hamming distance is high, she is going to say 0. So high means x and r are far away. Low means x and r are close together. So now you can see the intuition for Bob to pick ri. So if the Hamming distance is low, then ri is quite likely to be xi, right? Because this means strictly less than half the bits differ. So it makes sense to choose b equal to ri. If the Hamming distance is large, then this will not be a good b will not be a good reflection of ri, and that's kind of what we want here. So what we want is if xi equal to 1, then a and b will be positively correlated, and if xi equal to 0, then they will be negatively correlated. So positively correlated means low Hamming distance, negatively correlated means high Hamming distance. Okay, and this is accomplished without any communication, only using the random bits. Alice and Bob do not communicate their inputs with each other, or inputs or any information. So just to see why this is the case, let us define x minus I to be the bits of x excluding the ith bit, and similarly r minus I. All the inputs, all the bits except the ith bit. Okay. Now, so n is odd, as I already said. So n minus 1 is even. So x minus I contains an even number of bits, so does r minus I. So now let us look at the Hamming distance between. So let's just recap once again. B is Bob's input, which is chosen to be Ri. Alice's input is equal to 1 if the Hamming distance is low between x and r, and 0 if the Hamming distance is high. Okay. Now, x minus I is the bits of x excluding I, similarly r minus I. Now, if the Hamming distance of x minus I and r minus I is strictly less than n minus 1 by 2, or if it is greater than or equal to n minus 1 by 2, so n minus 1 by 2, x minus I contains n minus 1 by 2 bits. Sorry, n minus 1 bits, and n minus 1 is an even number, so n minus 1 by 2 is exactly half the number of bits. So this means it's strictly less than half, or it is at least equal to half. If in either of these situations, then the Hamming distance of x and r is already determined regardless of what ri is. Why is this? If it is strictly less than n minus 1 by 2, right? And now the Hamming distance of x and r, when we consider the Hamming distance of x and r, which in turn determines a value, we are just checking the ith bit. Now, does that contribute to the Hamming distance or not? So how do we check that? Is xi equal to ri or not? Now, even if xi equal to ri in this first case, this will become at most, so this is strictly less than n minus 1 by 2, so this will become at most n minus 1 by 2, right? And which is strictly less than n by 2. And in this case, it is already equal to n minus 1 by 2. Now, even if xi and ri don't contribute to the Hamming distance, xi and ri are identical. Let me just think for a minute. Okay, I think there is a typo here. This should be strictly greater than n minus 1 by 2. So, if it is strictly greater than n minus 1 by 2, then the Hamming distance between x minus I and r minus I also must be strictly greater than n by 2, because n minus 1 by 2 is an integer. So, if it is strictly greater than that, it must be the next integer, which also will be greater than n by 2. Okay, so there is a typo here. I apologize for that. Here it should not be greater than or equal to, it should be strictly greater than. So the point is, in this case, the Hamming distance is lower than the half, and even if xi and ri add 1 to the Hamming distance, it will still be lower than the half. And in this case, it is higher than the half. Even if xi and ri don't contribute, it will still be higher than the half. So xi is fixed by the input. Ri is going to be randomly chosen. So doesn't matter what Ri is going to be. The value of A is already decided regardless of what Ri is. Right? So what is the probability that A equal to B? Recall A is the input that was A and B are the inputs that were generated by Alice and Bob respectively. So what is the probability that A equal to B? Now B is Ri. It is the probability that A equal to Ri. Now A is fixed regardless of Ri because one of these two cases has happened. So since A is fixed, A is something that is already fixed. Ri will be 0 or 1 with probability half each. So now what is the probability that Ri will be equal to A? It will agree with A with probability half, whatever A is, 0 or 1. And Ri is independent of other things, so it doesn't matter what other things are. So the probability that A is equal to Ri is exactly half. If the Hamming distance is low or high, then A is already fixed regardless of Ri, and the probability that A equal to B is equal to the probability that A equal to Ri, which is half, because A is determined independent of the value of Ri. With using A is determined by the R minus I, all the other random bits except Ri. So the probability that A equal to B is half. In this case, there is no correlation between A and B. Right? There is absolutely no correlation, neither positive nor negative. But in the case when recall this is a typo here. This should be strictly greater than. In the case when the Hamming distance between x minus I and r minus I is equal to n minus 1 by 2, which is the only left out case, it's exactly half. Then what is the value of A? A is 0 or 1 based on whether the Hamming distance between x and r is high or low, right? And that, so now everything else is computes to exactly half. Now the value of A depends only on whether xi is equal to ri or not, right? So if xi equal to ri, then Hamming distance, this does not contribute to the Hamming distance, hence A is equal to 1. And if xi not equal to ri, then A is equal to 0. So now there is a direct correlation between xi being equal to ri and A and the value of A. So now if xi equal to 1, then note that A and B always agree. Why is this? If xi equal to 1, now let us consider ri equal to 1. Ri is the same as B, so then B is equal to 1, right? And when B is equal to 1, if xi and ri are both 1, then there is no increment to the Hamming distance, so it is low Hamming distance, so A is equal to 1. So B and A are same. If ri equal to 0, then B is equal to 0. And now ri equal to 0, xi equal to 1. So this contributes to the Hamming distance. So Hamming distance is more than half. So A is equal to 0. Again, A and B are same. Similarly, if xi equal to 0, then A and B always disagree. Why? Because if ri equal to 1, then B equal to 1. But then ri and x are opposite. So the Hamming distance increases, so A equal to 0. If ri and B are 0, then the Hamming distance remains less than half, so A equal to 1. So now again A and B are different. So if xi equal to 1, then A and B agree. If xi equal to 0, then A and B disagree. So A and B are positively correlated based on the value of xi in this case. So in case 1, A and B have no correlation. The probability that A equal to B is half. In case 2, the probability that A equal to B depends on the value of xi. It is equal to 1 if xi is 1, and the probability that A equal to B is 0 if xi is 0. So now, we will estimate the probability that A and B are same overall. So before that, let us estimate what is the probability that case 2 occurs, and what is the probability that case 1 occurs. The probability of case 2 happening. Case 2 happens when the Hamming distance between x minus I and r minus I is equal to n minus 1 by 2. What is the probability that this happens? So we have n minus 1 random bits, and half of them agree with x minus I and half of them disagree with x minus I. So we first have to choose which half agrees and which half disagree. And once we choose which half agree, now Ri is the r minus I is fixed because this is the half that agree and this is the half that disagree. So the half that agree must be identical with x, the half that disagree must be opposite to x. So the value of r minus I is fixed, and what is the probability that the r minus I is chosen to be exactly that? In each location, it gets that value with probability half. So the value that the probability that r minus I is equal to that is 1 by 2 power n minus 1 or 2 power minus n minus 1, right? And what is the probability or what is the number of ways in which this half is chosen? It is n minus 1 choose n minus 1 by 2, the probability of choosing this. Okay, and this probability, we are going to estimate this probability using our favorite Stirling's approximation. So recall m factorial was square root of 2 pi m times m divided by e whole power m, right? So I write that here. The numerator is straightforward. The denominator, I have two n minus 1 by 2 factorials occurring twice. So the square root 2 pi n minus 1, there are 2 times square root of 2 pi n minus 1 by 2. So I can, when you multiply square roots, you get the square, which is 2 pi n minus 1 by 2. And you have n minus 1 divided by 2e whole power n minus 1 by 2 occurring twice. So again, the divided by 2 gets removed from the power. So now you can see that this term and this term cancel out except for the 2 power n minus 1. Of course, we have the 2 power minus n minus 1 coming from here. So this and this get cancelled out except for the 2 power n minus 1 that I'm writing here. Square root of this 2 is taken to the numerator, and then square root of 2 pi gets cancelled. Square root of n minus 1 remains. So that's what we have. And these two are reciprocals, they cancel. And what remains is some constant divided by square root n. We assume n large, so square root of n minus 1 and n are kind of the same thing. And what is the constant? Constant is 2 divided by square root of 2 pi. So square root of 2 pi is 6.28. So square root of 2 pi is something bigger than 2. So c dash is going to be some number smaller than 1, but it doesn't matter that it is smaller than 1. So it's c dash divided by square root n for some constant c dash. We use n is large because I don't want to write n minus 1, so I'm just approximating square root n. You may be wondering why I took care of the square root 2 pi n here, and in all our previous binomial coefficients we did not retain this. That was because in all the previous binomial coefficients, the other factorial, the terms arising out of the factorials were distributed in such a way that there was a significant component in the numerator or denominator, rendering this square root 2 pi m factor very, very small and insignificant. So everything else gets, everything else results in such a big term in the numerator or denominator. So this becomes insignificant, so we ignored it. In this case, everything nicely cancels out. Even the 2 power n minus 1, everything cancels out. So now I cannot choose to ignore the square root 2 pi n minus 1 because that is the only thing that remains. So we need to be careful about that. So the probability that case 2 occurs is c dash divided by square root n for some constant. And again, n is large. And recall that we already assumed n is odd. Again, none of these are very unreasonable assumptions. Right? So we have probability. Case 1, the probability that a equal to b is half. Case 2, the probability that a equal to b depends on the value of xi. And probability that case 2 happens is c dash by square root. So what is the probability that a equal to b? We can condition it based on whether case 1 or case 2 happen. It is the probability that case 1 and the probability that a equal to b given case 1. That's probability that case 2 times the probability that a equal to b given case 2 happens. Probability, what is the probability that case 1 happens? It is probability that case 2 does not happen. It's 1 minus c dash divided by square root n. And this thing is half. Right? In case 1, probability that a equal to b is half. We have already seen that. In case 2, this is c dash divided by square root n. We just estimated that. And the probability that a equal to b in case 2 is 1 if xi equal to 1 and 0 if xi equal to 0. So now let us sum it all up. So the first term gives us 1 minus c dash divided by square root n multiplied by half plus c dash divided by square root n, property of case 2 happening, times 1 if xi equal to 1 and 0 if xi equal to 0. It's exactly this. So now we have two cases. If xi equal to 1, then we get this sum, half plus c prime divided by 2 square root n, or half minus c prime divided by 2 square root n if xi equal to 0. First case when xi equal to 1, second case when xi equal to 0. So that is a probability that a equal to b. Okay, so now we have completed the construction of a and b. Right, without any communication, Alice and Bob each get a bit. Right, using n, by looking at n random bits, they each get a bit, and the probability that these bits are same is slightly above half if xi equal to 1, which means the index equal to 1, and slightly below half if xi equal to 0. But this is just one bit, and we want to construct an instance of gap hamming. So now how do we construct an instance of gap hamming? We just repeat this. We just look at the next n bits, next n random bits, pick another a for Alice and another b for Bob, and you keep doing this. And you do this n prime, which is equal to q n times, to get n prime correlated bits, and we call it x prime for Alice and y prime for Bob. So where each bit of Alice is picked according to the process that we described, and each bit of Bob is also picked according to the process that we described. So for any bit, any index I in Alice's input and Bob's input in x prime and y prime, they are correlated positively if xi is 1 and negatively if xi equals 0. So what is the expected Hamming distance of x prime and y prime? So recall x prime and y prime are just this process done repeatedly. So it is a length. So it is the probability that they disagree. Right? It is the number of bits times the probability that they disagree. So if xi equal to 1, then the Hamming distance is going to be the probability of them differing is half minus c prime divided by 2 divided by square root n. So the Hamming distance is n prime multiplied by that. So you get n prime by 2 minus n prime c prime divided by 2 divided by square root n. So this is still square root n, because this is on the basis of how many bits are looked at to generate each bit. And when this is the answer, this is the expectation when xi equal to 1, and if xi equal to 0, then the Hamming distance is going to be this. The expected Hamming distance is going to be this. Now each one of them I rewrite it slightly differently. I write it in terms of some constant times square root of n prime, because I wanted to make this look like the formulation for the gap Hamming problem, where we had n by 2 minus c times square root n. So here n prime divided by 2 minus some constant times square root n prime. So the expected Hamming distance is going to be this, slightly below the half length if xi equal to 1, and slightly above the half length if xi equal to 0. Now we can apply a Chernoff bound. Again, this is a very routine application of Chernoff bound, and I'm not going to go into that. To give so this is a bound in expectation. We can make it a high probability bound. What is the probability that Hamming distance is strictly less than half minus, or strictly less than half minus c square root n, where you can take c to be a bit smaller than this quantity for the Chernoff bound to work. And if xi equal to 1, the probability that the Hamming distance is smaller is at least 8 by 9. And if xi equal to 0, the probability that Hamming distance is higher is 8 by 9. So which means we started with an instance of index and we arrived at an instance of gap Hamming instance, right? And the probability of there being an outcome that we don't want is low, right? That is 1 by 9. And we can set C to be anything that we want. So recall in the proof for the F0 bound, we had C to be 4. So just by increasing Q, you can get C to be whatever we want, right? Because C is going to depend on Q and C prime. So this means, so this completes the reduction. From an instance of index, we have created an instance of gap Hamming, which is going to behave in the way that we want. So we just estimate. So now, how does the reduction algorithm, the protocol look like? Given Alice and Bob, if they're given an instance of index, they could construct this instance of gap Hamming, and then and this requires no communication. And then they execute the gap Hamming protocol, and then they decide which side of the gap they lie on, and then they make the output. They say the output, and the probability of error in the gap Hamming problem plus the probability of error that is caused by the reduction will be low enough, and hence we get a randomized protocol for index. And we know that this protocol for index has to use linear many bits. Hence the protocol for gap Hamming also has to use linear many bits, because if you can do gap Hamming in sublinear many bits, then the index also will require sublinear many bits, right? So that completes the reduction, right? So I'll just very quickly recap. We used a reduction from gap Hamming to F0 for the estimation of F0. So we needed to show a randomized one round lower bound for gap Hamming, and that is what we are showing from the randomized one round lower bound for index. So we are reducing index to gap Hamming, and we are going to construct, given an instance of index, we are going to construct an instance of gap Hamming using no communication and only looking at the public randomness. So they divide the public randomness into n-bit blocks, and they look at each block one by one. So the first block, the ith random bit is Bob's input, and the n random bits are going to be compared with Alice's input x, and if it has lower Hamming distance, then A is said to be 1, and if it has higher Hamming distance, A is said to be 0. And what happens is that if xi equal to 1, which means if the index function computes to 1, then A and B are positively correlated, and if xi equals 0, then they are negatively correlated. And case 1 is when the rest of x except the ith index and rest of r except for the ith index have low Hamming distance or high Hamming distance. So this should be strictly greater than, in which case the Hamming distance between xi and ri does not come into the picture at all. So in this case, the probability that A equal to B is just the probability that A equal to Ri, which is independent of everything else, so it is half. And in the other case, the probability that x minus I and r minus I is, the Hamming distance is n minus 1 by 2, which is exactly half. So now the what is A depends on whether xi and ri agree or disagree. And what we can easily verify is that if xi equal to 1, then A and B are the same, and if xi equal to 0, then A and B are different. And the probability that the probability that we end up in case 2 depends on what is r minus I, and exactly half of r minus I needs to agree with x minus I, and that can happen in n minus 1, choose n minus 1 by 2 times 2 power n minus 1, 2 power minus n minus 1 ways, and that by Stirling gives us c dash divided by square root n. That's the probability for some constant. Probability that a equal to b is the probability that we are in case 1 times the probability that a equal to b in case 1 plus probability that we are in case 2 times probability that a equal to b in case 2. The first part is easy. This is 1 minus c dash divided by square root n, and this is half. The second part is c dash divided by square root n, and this thing depends on the value of xi. It is 1 if xi equal to 1 and 0 if xi equal to 0. And therefore we get this. And this is the essential part. So a equal to b, the probability that a equal to b is half plus c prime divided by 2 square root n if x equal to 1, and half minus c prime divided by 2 square root n if x equal to 0. So the correlation has happened here. If x equal to 1, there is positive correlation. If x equal to 0, there is negative correlation. Then all that happens is Alice and Bob just repeat this process qn times. So they will have to look at qn square random bits, right? Because for each time they need n random bits. So qn times n is qn squared random bits, and they get so this there is some is slightly deviated from half, but by choosing more and more by constructing a bigger instance, they are ensuring further separation from the expectation from the n prime by 2, and an application of Chernoff bound gives us that with high probability, the probability of the Hamming distance is low when xi equal to 1 and high when xi equal to 0, and that completes the reduction from index. So given an instance of index, you convert it into instance of gap Hamming, solve the gap Hamming. So there may be some error which is here 1 by 9 in the instance itself. It might not have translated the way we want. There will be some error in the gap Hamming problem protocol itself, which is some r epsilon. But these two errors put together also will be small, and hence this gives us a low error protocol for index. Since index requires linear bits, the gap Hamming also requires linear bits, and that completes the complete proof of the fact that the F0 estimation requires linear space if we need to approximate it with 1 plus or minus 1 by square root n approximation. I have already shared all these notes with you. It's just the video that was missing for the latter half. Okay, thank you.